Thanks for the invitation. I'm going to talk holomorphic. Sectional curvature of scalar manifold. Yes, sir. First, I will define what is holomorphic sectional curvature and what is the scalar quotient. Then I will state the main result. Then after that, the application of our main result to the moduli space of QR representation. Scalar manifold. That means X is a complex manifold, and this H is this family of smoothly varying complex inner product. This is the collections of tangents vectors, the tangent space, the complex vector space, and also such that we take the imaginary part of this metric. This is a two form. This two form should be closed. Means, the exterior derivative is 0. This is the definition of scalar manifold. So, take G is real part of this metric. Then this is a real inner product. So this defines a smooth metric, and this and the underlying smooth manifold. So now I will define what is the Riemannian curvature tensor. If you consider X as this underlying smooth manifold, then this is a vector space or vector space of this vector fields. This is the family of tangent vectors with vary smoothly. The Riemannian curvature tensor is defined as follows. For any three vector fields, the definition is nabla x nabla y of z minus nabla y nabla x of z minus nabla of this Lie bracket of x comma y of z. Here this is a Levi-Civita connection. So now I will define what is holomorphic sectional curvature. Holomorphic sectional curvature defined on holomorphic planes in the tangent spaces. So let x in x, and for each, this is a complex vector space. So for each two-dimensional real subspace which are invariant under this complex structure. So we define the holomorphic sectional curvature of x along P defined as follows: h of P of u j u. Here j is a complex structure, j square is minus identity. This R is the Riemannian curvature tensor. Then this is a tangent vector, this is also tangent vector. Now we have to apply the G is a smooth metric. This is a real number. So this is called holomorphic sectional curvature along the plane, holomorphic plane P. So let us see example. Cn, the usual complex manifold structure. Then the Kähler form for local coordinates is an open set, and for local coordinates the Kähler form we can write dxi wedge dyi, and this has a holomorphic sectional curvature. This is a flat, the holomorphic sectional curvature 0 everywhere. And the complex projective space with Fubini steady metric, it has a constant holomorphic sectional curvature everywhere. So why I give the two motivation why we should know about the holomorphic sectional curvature. The one is the general point. So we can, if you know the sign of holomorphic sectional curvature, we can get more information about the manifold. This author put in his paper. So Kähler manifold with positive holomorphic sectional curvature is always compact and simply connected. So we can get more information about the Kähler manifold once you know the sign of the sectional curvature. The second one is Kobayashi. So he calculated the holomorphic sectional curvature of moduli space of vector bundles, and suppose W is moduli space. Einstein Hermitian connection. And the holomorphic Hermitian vector bundle over compact Riemann surface X. Kobayashi proved that he constructed a natural complex Kähler manifold structure on this moduli space by holomorphic analog of symplectic reductions, and he proved that the holomorphic sectional curvature of this W is non-negative. So we have compute the holomorphic sectional curvature of Kähler quotient. I will define what is Kähler quotient. So we are in the following setup. So X is a Kähler manifold. And suppose G is a complex reductive Lie group. Example, the general linear matrix GLNC, and K is a maximal compact subgroup. Example, the orthogonal matrices, real matrices. Suppose we have holomorphic action on G on X, is holomorphic, such that the induced action K on X is Hamiltonian. These Hamiltonian actions come up with a special smooth map which is called moment map, and pi from X to this Lie K is a Lie algebra of K. This star is a dual. This is a moment map for this action. So let X naught is the level set by inverse of 0, and X1 is the G saturation of this phi inverse of 0 by this G. This set of all Gx, X in phi inverse of 0 and G in G. Then we have this natural map. So X1 to X1 mod G, I call this Y. So this map is P1. And we have this restriction map P0. So we have to assume this time why we don't have any structure. We have to assume this. We assume this action K on X, the free action. From the standard result, this free actions gives the natural Keller manifold structure. So from the free action, we have the following. One is this X naught is smooth submanifold. Number 2. So there exists a natural Keller manifold structure on this quotient Y. Natural means if you restrict the Keller form, pull back the Keller form on Y, we'll get the Keller form on X. For example, so we have a C star action on Cn, the usual action. Then the moment map here is minus 1 by 2 modulus of Z1 square modulus of Z2 square percent. So modulus of Z1 square is 1 by 2. Then the level set is S2n minus 1 sphere. The quotient is Sn2n minus 1. Sn is isomorphic to Pn minus 1. Now I will state my main reason. Hx and Hy. X and Y are before. Hs and Hy are holomorphic sectional curvature. of x and y. Then for all x in x naught and the for all horizontal unit tangent vector, we have the following formula which relates the holomorphic sectional curvature of x and y. The derivative of p naught at u minus 4 times. This is the second fundamental form. This is the main result, and the remark is, suppose if x is a flat metric, then the holomorphic sectional curvature is 0. In this case, we will get we know the sign of the holomorphic sectional curvature of y is greater than or equal to 0 if you assume x is a flat. Now we apply this main result to moduli space of QR representation. QR is a directed graph. And representation of QR is the data consists of vector spaces, finite dimensional vector space. For analytic study, we will take the C vector space, and this phi alpha is the source to this target. This A varies for all the vertices, and alpha varies for all the edges. For example, if we consider the QR is just 2 vertex and 1 arrow, then the representation of QR is just 2 vector space and 1 linear map. So now there is a notion of stability. We have to define what is stability for representation. We have to fix theta, which is with the real numbers. For fixing theta, the slope, we can define the slope of this representation is sum of theta A dimension C dimension of VA, sum of dimension of VA. Then so for moduli space, we will consider only stable representation. We have to restrict stable representations for getting nice moduli space. Representation is called stable, theta stable, if for every sub-representation the slope should be strictly less than slope of the V. This is for all sub-representations W. This is the definition of stability. Then M theta S, this is a moduli space, is isomorphism classes of theta stable representation of Q. So we fix the QR also, and we fix the parameter, This algebraic construction, moduli space construction given by King by GIT and one of our paper, Das, myself, and Raghavendra. So we gave a natural scalar manifold structure. So we apply our result to this moduli space of stable representation. So we get another result, theorem 2. So the holomorphic sectional curvature. The moduli space of stable representation is non-negative. We work with general quiver and we fix quiver and theta also we fix anything. So we did not put any restriction on that. Thanks.